Hey, welcome! Have you ever tried to write down a really, really big number, or maybe a super tiny one, and you just get lost in a sea of zeros? It's messy, it's confusing. Well, today, we're gonna demystify all of that. We're gonna learn the elegant trick that scientists use to tame these massive numerical beasts. Let's dive in. Just look at this number. That's the mass of our planet in kilograms. I mean, seriously, how would you even say that out loud? Forget trying to type it into a calculator. Writing it is a chore, and honestly, trying to do any math with it would be a total nightmare. This is the exact kind of problem that scientists and engineers were banging their heads against, and luckily for us, they came up with a brilliantly simple solution. So, here's our game plan for today. We'll start with why we even need this system in the first place, then we'll get into the rules, learn how to convert numbers back and forth, see it all in action, and wrap up with why this is so important. All right, so how do we deal with that ridiculous string of zeros? Well, there's a system designed specifically for this, a way to bring clarity and efficiency to the chaos. It's time to meet the hero of our story, scientific notation. Think of it like this. All we're doing is taking any number, no matter how huge or tiny, and breaking it into two simple parts. The first part is just a regular number that's always between 1 and 10. And the second part? It's simply 10 raised to some power. That's it. It's a super compact and powerful way to handle numbers that would otherwise be completely unwieldy. Now, for this whole system to work, everyone has to agree to follow a couple of really simple rules. This is what keeps everything consistent and, most importantly, easy for anyone to read and understand. And here it is, the magic formula. Every single number in scientific notation will look like this: some number a times 10 to the power of n. Now, here's the crucial part, the one rule you have to remember. That first number, a, has to be at least 1, but it has to be less than 10. And the exponent n is just a whole number. It can be positive or negative. Okay, let's see this rule in action. Look at that first pair. 426 times 10 to the 8th is perfect because 4.6 is right in our sweet spot between 1 and 10. But 45 times 10 to the 8th? Nope, that's wrong because 45 is bigger than 10. Same thing down at the bottom. The absolute value of negative 9.6 is between 1 and 10, so that's good to go. But 0.72 is less than 1, so that's a no-go. Honestly, getting this one rule down is like 90% of the battle. All right, enough with the theory. Let's actually get our hands dirty and start converting some numbers. This is where you'll see how simple and powerful this really is. The process is actually super simple. First, you just slide that decimal point over until there's only one digit that isn't 0 to its left. Step 2, you count how many places you moved it. That number, that's your exponent. And finally, the sign. Just remember this simple trick. If you started with a big number, your exponent is positive. If you started with a tiny decimal, it's negative. Easy as that. Let's try it with 82 million. Right now, the decimal is hiding at the very end. We're gonna move it all the way to the left, hopping over all those zeros until it's right between the 8 and the 2. How many spots did we hop? 7. And since 82 million is a big number, our exponent is a positive 7. So we get 8.2 times 10 to the 7th. So much cleaner, right? Now let's try a small number. Here, the decimal starts at the front. We need to move it to the right this time, past all those leading zeros, until it lands right after that first non-zero digit, the 1. We moved it 6 places. And because this was a tiny little decimal number, our exponent is negative 6. The final result, 1.35 times 10 to the negative 6. It's pretty clever, huh? You know what's even easier? Going backwards. All you have to do is look at the exponent. If it's a positive number, you're going to move the decimal to the right that many places, which makes the number bigger. If it's negative, you just move the decimal to the left, making the number smaller. So for this example, 3.7 times 10 to the 5th, we see that positive 5. That tells us, okay, move the decimal 5 spots to the right. You just add in zeros to fill the empty spots, and boom, you get 370,000. It's just doing the same process in reverse. Okay, so we've got the rules down and we've practiced the moves. Now let's see how this simple little system lets us make sense of the entire cosmos. So check this out. We've got the distances of 4 different planets from the sun, all in scientific notation. Now, just by glancing at this, can you tell which planet is farthest away? If these were written out with all their zeros, it'd be a total pain. You'd be sitting there counting digits and it would be so easy to make a mistake. But with scientific notation, it's incredibly simple. Here's the secret. First, you just look at the exponents. That's it. A bigger exponent means a bigger number, period. So Saturn and Uranus, with their 10 to the 9th, are way further out than Earth and Mars, with 10 to the 8th. Okay, so what if the exponents are the same, like for Earth and Mars? Then, and only then, do look at the decimal part. Since 1.5 is smaller than 2.28, Earth is closer than Mars. And just like that, we've ordered the planets. So what about doing math with these? Well, for adding and subtracting, there's one golden rule. The exponents have to be the same. So if you want to add 3.7 times 10 to the 5th and 2.3 times 10 to the 6th, you can't just add 3.7 and 2.3. You have to make the exponents match first. So we can change the second number to 23 times 10 to the 5th. Once they match, you just add the decimal parts like normal. And you know what? Multiplication and division are even easier. You just handle the two parts of the number separately. You multiply the decimal parts together, and then for the powers of 10, you just add the exponents. That's it. And for division, you do the same thing, but you'd subtract the exponents. It makes working with these huge numbers almost fun. So, we've gone through the how, but let's zoom out for a second and really lock in the why. Because this isn't just some neat trick you learn in math class, it's a fundamental language that helps us understand the world around us. So let's wrap this all up. At the end of the day, scientific notation is a beautifully compact system for handling numbers that are either astronomically big or microscopically small. The format is always the same, a decimal between 1 and 10 times a power of 10. And its real power is that it makes comparing and calculating these mind-boggling numbers totally intuitive. This is the language that scientists, engineers, and astronomers use every single day to make sense of our universe. You've just learned a new kind of superpower, the ability to take the universe's most extreme numbers and put them in their place. So I'll leave you with this question. Now that you can measure anything, no matter how big or small, what will you measure first? Thanks for joining me.